So Reinhard's going to be the first of 3 speakers talking about kinematics, rotation curves, and scaling relations of star-forming disks.
Thank you, Joe. It's good to be back to the yearly event, highlight of the year. All right, so yes, I'm the first of 3 talking about kinematics and gas in high redshift galaxies, and we all 3 are trying to give you the newest we have on our notes, so to speak. So the particular 3 issues I picked today for you is number 1, an update of our main paradigm, which we've been working with in terms of the internal physics of these high redshift gas-rich galaxies, and that's the, if you like, the marginally stable gas-rich disk Q, Tumor Q, about 1 paradigm. The reason I picked that is because although most of us still feel this is the right, overall theme, there have been some questions on the theory side, and you've heard that, I think. But I would like to sort of address a few issues which we can, at least on the observational side, because questions have come up, in fact, this year in other conferences where we've debated some of the issues of substructure and the kinematics, which I'll like to touch on. Then I'll introduce, in a sort of broader context, the 2 new, where I feel two new areas of research, which are just beginning. And which I believe will keep a number of us busy in the years to come. One is to go out from the galaxies into the halos and try to measure through kinematics the properties of the halos and connect up with the dark matter. And I show you what we have at this point. And then go inward with ever higher resolution to study kinematically, in fact, some of the physics which the simulations are also currently getting up to. But let me start with sort of a general statement on the status of the field. So over the last few years, we've seen the beginning of what I would call a very substantial revolution. Good morning, Sandy. In spectroscopically studied galaxy samples, where there were only a few 10 years ago. Over the last 3-4 years, 3 instruments, 2 in particular, have really revolutionized the field through multiplexing. One is KMOS on the VLT, which is a multi-IFU, multi-symphony, if you like, instrument with 24 IFU units at the same time. MOSFIRE, slit spectrometer, very, very sensitive instrument on the kick. And for lower redshifts, the optical equivalent, so to speak, super machine called MUSE, also on the VLT. So we are beginning to see data sets from all these instruments coming in. And so it's possible to construct diagrams like this, where one puts some small fraction of one's galaxies in the stellar mass star formation rate plane. I'm emphasizing this. We're not showing all the galaxies anymore because they don't fit on the pictures. Here, this is to show, broadly speaking, the velocity fields and that they are generally ordered. So if I would summarize in 1 slide what we have learned over these last few years and what is now apparently consensus, then from, broadly speaking, about 2,000 galaxies at seeing limited resolution. So that's just under sort of half the resolution, or half the size of the galaxy or so. And then for a smaller subset at adaptive optics resolution, then most people would say, a very significant number, whether it's 50% or 80% doesn't really matter, but a very significant majority of the high redshift galaxies on the massive end, okay, massive end, not the low mass end, which is less studied, can be described as rotationally supported turbulent disks. And that goes throughout the community. There are some people who disagree, okay? And we need to look, of course, at the dissents as well as the consensus. And I'll comment on that just a little bit. So I don't want to go more in detail. I've talked about this before. This is sort of the backdrop. We now believe we have rotationally supported largely, but also very turbulent disks. Absolutely truly, there will be interlopers, there are mergers, there are disturbances, all of this, but the first order, please, the first order picture is that of rotationally supported with some very significant amount of random motion. So let me just take one slide then to re-educate you or remind you of what gives us a right to call some galaxy rotating? What are the points we need to have fulfilled? And here's a picture of, on the left side, the brightness distribution or mass distribution. In the middle of the velocity field projected on the sky at some inclination. And on the right side, the second moment, the dispersion. You could go on, and that will happen in the next years. The higher moments, H3 and H4, are just about to come. The data sets are now good enough, but it hasn't yet happened, so I don't show it here. So this is a model galaxy of an exponential n equals 1 Sérsic index disk. So the criteria for rotating disk structure in order of complexity and difficulty are, number one, if you look at a galaxy, it ought to have a smooth velocity gradient. So if you see a very distinct jump, then that should make you worry. Second, the inclination corrected rotation velocity over what you might want to call the mean outer disk dispersion should be greater 1.5 or 1 or 2, whatever you would like to say. Now here there's some technical devils, namely the sigma naught. If you go into the literature, there's unfortunately a widespread of definition of that sigma naught. For instance, some people use, and in fact in the absorption, stellar absorption literature, all people assume that sigma naught is the average total velocity dispersion of the galaxy. Now, that is not what I mean here, okay? Because these galaxies are rotational supported. We should first subtract the rotation, so to speak, and look then at what's left over. And what's left over can be best studied, in my view, in the outer parts. But there could be dependencies on radius which we don't know. So this is actually a fairly tricky quantity which you would measure out here and out here once you have subtracted the beam smeared rotation. We come back to this, beam smeared rotation. Next one is the velocity dispersion peak should be at the center of the kinematic systemic velocity of what you want to call the velocity gradient, okay, where V cis is equal to 0. The next one, the axis of line of nodes, which is this direction here, should be the same as the morphological major axis. Now, when you go to a low inclination, so face on, we see empirically that this is often violated because the light distributions from which you deduce the morphological axis is in reality influenced by clumpiness, asymmetries, etc., etc. So this can be quite tricky, if the galaxy is not at a high inclination. It's getting more difficult now. As you go out here, then at least for a simple rotating disk galaxy or a rotating disk galaxy embedded in a dark matter halo, there should be detection of a plateau of velocity on either side of the center, which in a disk is at about 1.3 to 1.8, the effective radius of the disk. Now this one, you will see quite a bit of later in my talk and in Hannah's talk, is where the state of the art is right now. If you go to data sets in the literature, you won't find that much. Many people integrate only for 1 to 2 hours on single objects and often do not get to this asymptotic part, the danger being obviously that you underestimate the rotational velocity. So for Tully-Fisher studies, which Hannah will report, that can make a big difference from paper to paper what the conclusions are. The next one is the dynamic centroid. So we agreed that this was here. Should agree, or plausibly should agree, with the stellar surface density, not stellar light, okay, stellar surface density centroid, if there is indeed a central object which we might want to call a bulge. Now, lower mass galaxies don't have that, so you might look for it and you won't find it. So be careful here, young low mass systems, that is not easily possible. The next one is, and that's getting really difficult, is to see the spider diagram, right? So the more complicated isovelocity contours, and then in particular, that's the morphological inclination, which you derive from the major to minor axis ratio, should be equal to the inclination derived from the isovelocities. Very few galaxies have quality diagrams. You will see one where this is possible. So here's the list. And most studies penetrate about to this level, at which point, of course, a criticism or a sort of question, is this really true that its rotation is about, is very well, very well posed. Okay, so I want to touch as number one of the more specific issues, the issue of the instability, the gravitational instability, and in gas-rich disks with rotation, there are two scales. The upper scale is beyond the so-called Tumor scale, at wavelengths longer than Tumor scale. There cannot be gravitational fragmentation because the rotation stabilizes the galaxy. And at scales less than the gene scale, there will also be pressure support and no gravitation collapse. And between these two scales, from the stellar scale, so to speak, from the protostellar scale all the way to the Tumor scale, you have instability. So that's been the picture, and the instability picture is such that when you look at the ratio of the sizes of the instability to that of the disk scale, which turns out to be the same as the velocity dispersion over the disk velocity, then this is very closely connected to the gas fraction in this disk. It's a very simple relationship with a number q, which is in the vicinity of 1. I do not want to discuss now the slight deviations which you would expect. So this is the sort of the basic number we're looking for, and there is a scale here which we should be able to measure with current technology. The gene scale, of course, you cannot measure. Now, there have been some papers lately which point out, oh, well, maybe this scale here is so close to the resolution of most people's data that is nothing, there's just a beam smeared effect, ghost kind of a thing, and has no physical meaning. And by the way, they say, what about scales less than this this Tumor scale? So that's an important factor. The next one is that in such a disk, the torques, the interactions between the largest fragmentation scales, so these Tumor scale clumps, lead to an in-spiral radial motion of the gas and the stars, and that can be fairly short if V over sigma is small, and V over sigma is small if gas is large. So the high redshift disks have this very interesting feature that there are new timescales coming into play, transporting material through the disk. Okay, so now testing that, for instance, in terms of the velocity dispersion. We know, and Linda will tell you, that the gas fractions go up with redshift, so we would expect that sigma goes up with redshift. And indeed, we, Susan Cassin and others, have looked at this dependence, and here's from the literature between redshift 0 and high redshift various data sets, which I don't want to comment on. Our KMOS 3D survey with about 600 galaxies in green here, with mean values at given redshifts here in black. So Susan and we agree, and most other people I think agree, there's a trend of the medians very clearly. So velocity dispersions go up with redshift such that in fact what you would expect here from sigma naught proportional to F gas is reasonably fulfilled. That's a good success, I would say. But what about the scatter? The scatter is much larger than you would expect. Now, there could be hidden variables. Indeed, star formation surface density may be such a variable, but we haven't really figured that out, and that's something we should. So not all of this is due to measurement error. This is truly, there is scatter which we don't understand, and Mark Krumholz and others are working on the potential theory. Now, it's very important whether or not this change here is gradual or not. because we're connecting this picture to one developed at low redshift through archaeology. And there, we know since Gilmore and Reed that there is a second component to the stellar system in the Milky Way other than the thin disk, which is the thick disk. And the thick disk has two components. Sorry, there's a thick disk and a thin disk. Well, if this galaxy were one of those, you would expect there are multiple thick disks here at different redshifts producing, and of course changing in time and so forth. So we would expect a more gradual change, two components. Now it's interesting that Bovie and Ricks do exactly come up with that. And so the relationship to the story of the thick disks, or whether we have several thick disks or not, and this one are closely interwoven. Don't have time to discuss this here, and so let me go on to the tumor scale. So the tumor scale, can we look below the tumor scale? And the answer is, with current technology, you really need a massive galaxy which is lensed in a way which is well enough understood that you can look at the spatial structure, the power spectrum density. Here's one of the very few ones which is moderately stretched in this direction, mass of 10 to the 11 solar masses. This is the HST image. This is the H-alpha image with symphony in adaptive optics mode. So here we have along this direction, the stretch direction, 400 parsec resolution. So that's about 4 times better than what we usually have with adaptive optics in this big massive galaxy. So if you de-stretch, this thing is a pretty face-on system actually. And indeed, the rotation velocities are small, but they're clearly there along the stretch. Velocity dispersions are pretty constant in the system. So here you can now measure the fluctuation spectrum in this direction, and that's done here. This is the power spectrum of the noise. The resolution is around here, but you clearly see this hump here. So that's the tumor scale in this system. So I think, yes, we do see the tumor system. Next subject is new avenue determined mass distributions. So what we want to do is use rotation velocities like in the local universe to get out there. And in fact, with the KMOS survey, for instance, where we have long integrations, we're beginning to be able to do this, but you do need pretty long integrations. You can look at the inner disk dynamics, which is what many people do, but then as one knows, you have to know what the M/L ratio is in order to say something about dark matter. So that's difficult. Lensing, yeah, very, very good, but very few massive lenses. Individual or stacked outer rotation curves is very challenging, and I show you the first results. You need integration times of 10 hours or more on 10-meter class telescopes. And then outer halo tracers, satellite kinematics is not yet been attempted. It's also difficult because the satellites are faint, but this can be done. This can be done now at some level. Tully Fisher is what, yes. Okay. So here is one galaxy. You see the H-alpha distribution, the velocity field, the velocity dispersion field, HST, and the residual data set. So that's a system where we have 47 hours integration. And when analyzing, you then have to model the galaxy with a disk, a bulge, and some dark matter. In this case, we used NFW. And there's two extremely important issues at high redshift. One is the finite resolution, the beam smearing, and the second one is what we call asymmetric drift, which is the correction for the fact that the circular velocity is not equal to the rotation velocity due to the fact that there's very substantial pressure due to the random motions, the sigma term, and that increases with radius if sigma is constant. So the asymmetric drift has to be considered. Yes, I'm trying to work this, but I won't finish at 0 minutes. Although I can, but then you won't get the story. So here is the data along the major axis. Here's the rotation curve. That's the velocity dispersion curve, and that's a cut perpendicular. So here we can actually make this test of the inclination from velocities indeed is low and is the same as in morphology. The rotation curve does drop here apparently, and so we can actually fully model this system. And here's in the end, the modeled rotation curve. Then there is the beam-smeared final rotation curve. And you see here that the asymmetric drift is what makes the difference in the outer parts between this and that. So that's why it's very important to take that into account. And also the inner parts, of course, are beam smeared away unless you take that into account. So people who take rotation curves at high redshift and then draw straight lines to infinity just don't know what they're doing. You cannot do this. You have to actually go beyond this. So here's a bunch of 6. Again, the main point is, whilst the data seem to, look like pretty flat here, the intrinsic rotation curve is sloping in this galaxy all the way to the center, all the way to the center. You want me to completely shut down? Yeah? No. Okay. Yes. Okay. We've done similar work on stacking rotation curves with a similar result. I would want to make a comment, I'm happy to discuss this privately, that the fact that there is the asymmetric drift here gives a unique opportunity to break the famous halo disk conspiracy. And I'm happy to explain that, but I don't have the time here. So that's the sort of the summary of the rotation curves can be found in the Nature paper this year. If you average them all together, you see that in fact, not only is it not flat, it is not a Freeman disk. That's this asymmetric drift, which you have to get here. And then in the end, and Hannah will discuss this more, the result is that you cannot have much dark matter in the disk. I'm not saying you cannot have much dark matter. I'm saying in the disk. Okay, thank you.
Okay, we have time for 2 questions. Abhishek is the first to ask a question.
I would just like to mention that in cosmological simulations, we do find a fraction of the galaxies that have a similar kind of funny rotation curve, but not all the galaxies, and not the majority of the galaxies. A minority of the galaxies do this, so that's something we need to understand. But one technical issue that may make the discrepancy even worse. You use the correction where the dispersion term grows linearly with radius, which is true for a thin disk. When we try this approximation in our cosmological simulation, it fails. The growth is slower than our. So this may make the discrepancy even higher.
Yes.
Sandy?
I have kind of an analogous question. This is really just a completely naive question. And that is that the extent to which truly classical instability arguments actually work in objects that are not only puffy, as you have stressed, but also perhaps not very much in equilibrium. So maybe we should talk about this in the discussion.
Sandy, this is why I brought this subject up, because there is ongoing intense discussion between the theorists and the observers, which is now penetrating from the first order level, where everyone seemed to be happily agreeing 5 years ago or 3 years ago, to deviation from that in that sense. What happens in the nonlinear regime? Do we see collapse motions? Do we see rotation of the column? So the answer observationally currently is not, and yet theoretically it's expected. So these are interesting questions. Obviously, you will have to pick up on, but you can imagine what this means. This means having 300 parsec resolution, high quality spectra. You better have a big telescope.
Well, we're going to have JWST pretty soon. Okay, I guess you have
JWST won't do it.